All right, let's dive in. Today, we're going to pull back the curtain on a scientific technique that literally makes the invisible visible. So get ready for what I like to call the Great Molecular Race, an introduction to gas chromatography.
So, have you ever really thought about it? How can someone take a single drop of perfume and tell you every single one of the hundreds of ingredients inside? Or how do environmental scientists find one specific dangerous pollutant in the air we breathe? How do they find that one tiny needle in a giant molecular haystack?
Well, the secret is an incredibly clever and powerful technique called gas chromatography, or GC for short. You can think of it as the ultimate molecular detective, the tool that scientists use to solve these kinds of complex chemical puzzles every single day. To really get how this works, we've got to start with the basics. So, what is gas chromatography, really?
At its heart, gas chromatography is all about separation. It's a method that takes a really complex mixture, like the scent of a rose or a sample of river water, and it carefully teases apart every single chemical component inside.
Now, to make this super easy to picture, we're going to use one simple idea for this whole explainer. I want you to imagine gas chromatography as a super high-tech, microscopic racetrack, but it's built just for molecules. And in this race, every single molecule is a competitor. Okay, so let's follow our little molecular racers from the starting line all the way to the finish and see how this race actually plays out.
So, how does this race actually work? Well, first, our sample gets heated up until it turns into a gas. It gets vaporized, and then it's injected right at the starting line. Next, you need a little push. An inert gas, usually something like helium, acts like a constant wind at their backs, pushing all the molecules forward. The racetrack itself? It's a very, very long and super thin tube called a column. But here's the catch. This is no simple track. The inside is coated with a special liquid called a stationary phase, which acts like a sticky obstacle course for the molecules.
Now, this quote gets to the real science of it. Partitioning sounds complicated, but it just means every molecule has to make a choice. Do I spend my time moving forward with the gas, or do I hang out and interact with that sticky obstacle course? Some molecules just aren't interested in the coating and they zip right past, while others really like it and get slowed way down.
And not all racetracks are the same. The old school versions called packed columns were kind of like a tube just stuffed with sand. But today, we almost always use what are called capillary columns. These are amazing. They're just hollow tubes with an incredibly thin, even coating on the inside wall. It's like upgrading from a bumpy dirt road to a perfectly paved Formula One circuit. They're way more efficient and give you much sharper, faster results. The cool thing is, scientists are like the race officials here. They have a bunch of knobs they can turn to control the outcome. They can crank up the heat to make everyone speed up or change the flow of the gas. But what really separates the molecules comes down to two main things. First, how easily it turns into a gas. Lighter molecules with low boiling points just want to fly. And second is something called polarity. You can think of it as chemical stickiness. If a molecule is chemically similar to the track's coating, it's going to stick to it more and get slowed down. And that difference in speed is everything. It's how they all get separated. Okay, so our molecules have raced down the column. The fast ones are coming out first, the slow ones are trailing behind. They're all perfectly separated. But this is all happening on a microscopic scale. How in the world do we actually see who won the race and who came in second and third? This brings us to the most exciting part, the finish line. This is where we finally get to see the results and figure out exactly who all our molecular competitors were. Right at the very end of that long racetrack, there's a device called a detector. And if the column is the track, then the detector is basically a super-sensitive, high-speed finish line camera. Its job is to snap a picture of every single molecule right at the moment across the line. And just like in sports photography, you have different cameras for different jobs. An FID, or flame ionization detector, actually burns the molecules as they come out. It's fantastic for anything with carbon. A TCD, a thermal conductivity detector, is more of a universal tool. But the undisputed champion of detectors is mass spectroscopy, or MS. This thing is the most powerful camera you can get. It doesn't just see a molecule cross the line, it smashes it into pieces and then weighs every single fragment. This gives you a unique fingerprint that provides a positive, absolute identification. It's incredible. So what do these results actually look like? Well, they're printed out as a graph called a chromatogram. You can think of this as the official race results sheet. Time is on the bottom axis, and every time a molecule crosses the finish line, the detector zaps it and creates a peak. The fast molecules show up as early peaks on the left, and the slow ones appear later on the right. And the size of the peak?
That tells you exactly how much of that molecule was in your sample.
So, now we know how the race works, but why does any of this matter? Let's take a look at where this amazing technology actually shows up in our everyday lives. The truth is, GC is everywhere, constantly making the invisible visible. It's the tool that finds tiny traces of pesticides in our food and water. It's how food scientists can identify the hundreds of different compounds that create the perfect coffee aroma. In forensics, it's used to identify substances found at a crime scene. From making sure our medicines are pure to developing the perfume you might be wearing right now, GC is one of the true workhorses of modern science. Now, of course, no technique is perfect for everything. GC is an absolute powerhouse. It's incredibly sensitive, it's fast, and it's very accurate. But it has some rules. The biggest one is that your sample must be volatile. That just means it has to be able to turn into a gas when you heat it up without falling apart. If your molecule can't handle the heat, well, it can't enter the race.
So if there's one thing to take away from all this, it's this. Gas chromatography gives us a window into the chemical world all around us. It gives us this remarkable ability to take a complex, jumbled-up mixture, cleanly separate out all of its individual parts, and then identify them, one by one, with amazing precision.
And that leaves us with a final thought. From the air you're breathing right now to the dinner you're about to eat, you are completely surrounded by complex chemical mixtures. So, if you had this technology in your hands, what invisible mixture in your world would you want to analyze first?